Okay, perfect. So it's my pleasure to introduce Sue Sierra, who will be speaking about ideals of enveloping algebras of loop algebras.
Right. Great. Well, thank you very much for the invitation. I apologize for the technical issues that delayed the start of the talk a bit and also will mean that I can't um, do that. I'm going to be lecturing off of a PDF instead of off of slides that I can highlight as I go. Um, so, yep. So this is joint work with Alexey Petukhov. Um, So I have been thinking largely with Alexey, some with other people who you'll hear from in this talk for the past few years about the two-sided structure of enveloping algebras, of infinite dimensional Lie algebras. Um, and this is because the one-sided structure of the enveloping algebra of an infinite dimensional Lie algebra is conjecturally always horrible, that is, not Noetherian, and this conjecture is getting closer and closer to being proved. On the other hand, for many examples of infinite dimensional Lie algebras that people are interested in, the two-sided structure seems to be very rich and also much better behaved. So what I'm going to tell you about today is what is known about two-sided ideals in enveloping algebras of loop algebras. So I'm going to start by talking about the kinds of Lie algebras I'll be looking at. Then I'm going to tell you the question that I want to answer, and I'll tell you the answer that we've arrived at. And then I'm going to talk a little bit about the proof of this partial answer to the question. So let me start by telling you about the Lie algebras that I'm working with. So in this talk, fractor G is always going to be a finite dimensional, simple, complex Lie algebra. And I'm most interested in the loop algebra of factor G. So I can think of this as maps from C star to G, but it's easier to think about it as Laurent polynomials in the variable S with coefficients in G. So this is a Lie algebra under the natural Lie bracket. It's really the only sensible way to combine two of these Laurent polynomials. So I've got x and y in the underlying Lie algebra G, and I've got x s to the I, y s to the j. Then to get their Lie bracket, I combine x and y with the Lie bracket in the finite dimensional Lie algebra, and then I multiply by the product of the polynomials, so by s to the I plus j. Now, closely related to the loop algebra of G is this affine Lie algebra, which I'll call G hat. So this is a one-dimensional central extension of the loop algebra. And in fact, I can define it by saying it's the unique non-trivial central extension of the loop algebra. But I can also tell you the Lie bracket. So as a vector space, G hat is loops on G direct sum, a one-dimensional space generated by a central element C. And then the bracket is, okay, I've got an x s to the I plus something times C, a y s to the j plus something times C. C is central, so the somethings times C don't matter. But the x s to the I and y s to the j, they bracket together to get, I get the bracket in the loop algebra, x, y, s to the I plus j. And then there's a scalar times C, which is effectively, it comes from the the killing form on the underlying finite dimensional Lie algebra modified as you see here. So those are the Lie algebras I'm interested in. Now let me tell you about the associative algebras. I'm sorry, I know this is a non-associative seminar, but I'm mostly a ring theorist. I'm mostly interested in associative algebras. So even though I have my nice non-associative Lie algebra, I want to turn it into an associative ring. So this is the universal enveloping algebra, say, of G hat. So what is that? Well, it's a tensor algebra on G hat, factored by the relations where I declare the commutator in the ring of two elements of G hat to be the same as the Lie bracket. So this is set up so it's an associative ring and it has the same representation theory as the Lie algebra. So if you're interested in representations of G hat, but you'd rather think about an associative algebra for some reason, well, you can look at modules over this enveloping algebra. So what is this ring like? Well, the thing that's quite easy to see is it is neither left or right Noetherian. This really is because it contains an infinite dimensional abelian subalgebra. For example, the subalgebra generated by all the xs to the I. So I fix an element x in my underlying finite dimensional Lie algebra, and then I look at all the non-negative powers of s times x. Those all commute. So inside this enveloping algebra, I have a big polynomial ring in infinitely many variables. And if I take an infinitely generated right ideal of that big polynomial ring and then just multiply up to get a right ideal of the enveloping algebra, it continues to be infinitely generated. So this is an example of a right ideal of the enveloping algebra of G hat that cannot be finitely generated. So there we're proving that U of G hat is not right Noetherian. And similar examples, of course, work on the left. So the one-sided structure of this enveloping algebra is a mess. And it's so easy to see it's a mess that the one-sided structure is in some sense not very interesting. The two-sided structure, though, well, it's a lot more structured. So let me tell you what is known, or what's in the literature about the two-sided structure. This is from a paper of mine with Reka Biswell, which is just coming out in Algebra and Number Theory, but appeared on the archive in the beginning of 21. So first of all, if I take a non-trivial central quotient of U of G hat, so in other words, I factor out C minus a non-zero scalar lambda, then that ring is simple. So there's no two-sided ideals at all. And then secondly, well, the heuristic for the second part of this theorem is that ideals, by which I mean two-sided ideals, in the enveloping algebra of the loop algebra are big. So let me tell you what that actually means. Well, first of all, the enveloping algebra, the loop algebra, that's the same thing as U of G hat factored by C. So this fits into this family of central factors of U of G hat. And if I have a non-zero two-sided ideal in the enveloping algebra of the loop algebra, then the quotient U of LG factored by I has finite growth. What I mean by this is that given I, there's a integer d such that for any finite dimensional subspace of U of LG factored by I, let's call that V, if I take the products of V with itself n times, measure its dimension, and then look asymptotically at what that happens as n goes to infinity, eventually that dimension is going to be bounded by n to d, n to the d, the integer d that I picked. So this says that the growth of U of LG factored by I, the Gelfand-Kirillov dimension, if you want to be technical, is at most d. Usually that says that we say that that means that this ring has polynomial growth, but in this talk I'm going to say it has finite growth. And this is interesting because the enveloping algebra, the loop algebra, has infinite growth. It looks like a polynomial ring in infinitely many variables, and it's easy to see that if you have a big polynomial ring, then there's no integer d that's going to work for all finite dimensional subspaces. So when I say ideals in U of LG are big, what I mean is that U of LG is a huge algebra with infinite growth, but if I factor out by any ideal, that ideal is so big that it knocks this infinite growth algebra down to finite growth. And we say this, in our paper, we say this means that U of LG has just infinite growth. Right? It has infinite growth itself, but any proper factor has finite growth. So this is what is in the literature about two-sided ideals in U of G hat. And the open questions are clearly about two-sided ideals in the enveloping algebra of the loop algebra. So, well, what we know already suggests a question, because we know that ideals in the enveloping algebra of the loop algebra are big. Since they're so big, maybe there's not room for there to be a lot of them. Maybe the two-sided structure is controllable. Is the ideal lattice of the enveloping algebra of the loop algebra, is it tractable or well-behaved in some way? So more formally, what is the structure of two-sided ideals of the enveloping algebra of the loop algebra? So before starting to answer this question, let's look at some ideals, and we're going to get our ideals as kernels of homomorphisms. So there's one very obvious ring homomorphism floating around, which I'll call phi1, which takes the enveloping algebra of the loop algebra, that is, the loop algebra, remember, is Laurent polynomials with coefficients in G, and I'm just going to, instead of taking the enveloping algebra of loops over G, I'm going to map that to loops over the enveloping algebra of G. In other words, I'm going to take the enveloping algebra of the finite-dimensional Lie algebra G, and then take Laurent polynomials over that ring. So this is an obvious thing to do. I want to keep track of my variables here, so I'm going to use T to be the Laurent variable for enveloping algebra, Laurent polynomials over the enveloping algebra, and I'm going to use S to be the Laurent variable, the loop variable, just for the Lie algebra. But this map just sends xs to the I to xt to the I, where x is an element of my underlying Lie algebras. This xs s to the I, you think of it as just an element of the loop algebra of G. So this is a very obvious ring homomorphism that's kind of floating around in this picture. But you can soup this up to get a whole family of ring homomorphisms, which are called phi sub L. So phi sub L maps the enveloping algebra of the loop algebra to Laurent polynomials in L variables over the enveloping algebra of L copies of the underlying finite-dimensional Lie algebra. So here I take some xs to the I, and I map it to x in the first copy of G times t1 to the I, plus, 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 x in the lth copy of G, tl to the I. So really what I'm doing here is the enveloping algebra of G direct sum L is the same thing as the L-fold tensor product of UG. So in here is the co-multiplication on the enveloping algebra of G. So we've got these homomorphisms floating around. They turn out to be very closely related to the representation theory of the loop algebra. So to explain this, I want to tell you a little bit about representations of the loop algebra. So let's start with a representation V of the finite-dimensional algebra. This is a different V than the V I had earlier. Sorry about that. Representation of the finite-dimensional algebra. This gives you an evaluation representation denoted V sub A of the loop algebra. So what is this? Well, I'm going to map the loop algebra to the underlying Lie algebra by sending the variable s to the scalar a, and then I'm going to have the underlying finite-dimensional Lie algebra, which I've now mapped to, act on V. So this is cheating slightly, right? Because the loop algebra of G, there's no s. You can't get s by itself. S only appears when it's multiplied by an element of the finite-dimensional Lie algebra. So really what I'm doing is I'm mapping the enveloping algebra of the loop algebra through phi1 to Laurent polynomials over the enveloping algebra. Now, in that new ring, I have itself, and then I'm t, and I'm realizing I should have said that this A had to be a non-zero scalar for this to work. So, so this phi 1 is sort of the universal map for evaluation representations. But also, given L representations of the finite-dimensional Lie algebra and L scalars, I can then tensor together. I now have L different evaluation representations, V1 sub A1 through VL sub AL. I can tensor them together, and LG, and so U of LG, act on this tensor product, and this action, you can see, factors through this homomorphism phi sub L. So these tensor products here, they're important because expressly classified finite-dimensional irreducible representations of loop algebras, and they're all of this form, a tensor product, finitely many, finite-dimensional in this case, evaluation representations. And the kernel of phi L is the intersection of the annihilators of all these L-fold tensor products of valuation representations to the representation theory of the loop algebra. And of course, also, these kernels are two-sided ideals in the enveloping algebra. So we now have enough information to give an assertion, which, if you remember, is the ideal lattice of the enveloping algebra of the loop algebra, is it tractable? So it's no and yes at the same time. So here's the enveloping algebra of the loop algebra does not satisfy the ascending chain condition on two-sided ideals. So just like we saw it's not one-sided Noetherian, it also isn't two-sided Noetherian, right? There are infinitely generated two-sided ideals in this ring. In fact, the image of any phi L doesn't satisfy the ascending chain condition on two-sided ideals. So it's not, you don't actually have to look at the full enveloping algebra. You can look at its images under these phi Ls. But so that's no, it's not tractable. Here's the yes answer. If I've got a non-zero two-sided ideal in the enveloping algebra of the loop algebra, let's call it J, then J contains the kernel of some phi sub L. So these phi sub L's are cofinal in the ideal lattice. And so on the one hand, if you want to understand ideals, then part 3 here says, well, it's enough to understand ideals of the image of phi L. So that's good. That says the ideal lattice is tractable. But then, of course, parts 1 and 2 say it's hopeless to understand two-sided ideals in the image of phi L. So I'm not sure whether this theorem qualifies as good news in the end or not. But this is the structure that we have. So what I'm going to do for the rest of the talk is tell you a bit about the proof of this theorem. But first of all, are there any questions about the statement of the theorem or anything I've said so far? Okay. So let me move on then and tell you a bit about the proof. Of the theorem. So I'm only going to give this proof for SL2, which I'll have with the standard basis E, H, and F. So let me first of all tell you about the bad behavior, the non-Noetherianity. So I'm going to show you what's wrong with the image of phi 1 and why the image of phi 1 does not satisfy the ascending chain condition on two-sided ideals. So I'm looking for two-sided ideals in the image of phi 1. So it's natural, an obvious place to find two-sided ideals is just looking at ideals of the center of the image of phi 1. So let's work out what the center of the image of phi 1 is. Well, the image of phi 1, of course, sits inside USL2 Laurent polynomials over USL2. So first of all, what's the center of Laurent polynomials over the enveloping algebra of SL2? Well, there T is central. T inverse is central, and then the other thing that's central is the Casimir element of the enveloping algebra of SL2, which generates the center of USL2. And it's not hard to see that the center of this ring is just generated by the Casimir, which I'm calling omega, and by T and T inverse. Then one can also check that the center of the image of phi 1 is the intersection of the image of phi 1 with the center of this overring. So it's the image of phi 1 intersected with polynomials in omega t and t inverse. So which elements of that ring do I get in the image of phi 1? Well, I certainly get the Casimir. I get Casimir times powers of t. And of course, Casimir times powers of Casimir. The thing I don't get is t. Right? I never have t by itself. Remember, I sort of cheated when I defined evaluation representations. I said I was setting s, the variable s, to be equal to a, when in fact I never had the variable s on its own to get my hands on. So I never have t by itself. So what I end up with in the image of phi 1, in the center of the image of phi 1, is constants, of course, and then I get the ideal of the center of the overring generated by omega. So I get anything times omega is in the image of phi 1, but stuff involving just t and not involving omega isn't in there. And this omega times the center of the overring, this is going to be an infinitely generated ideal of the center. If you think about it, you've got, from omega, if I'm trying to generate my ideal, well, okay, so I put in omega as a generator, then omega times t is in my ideal. But I can't get omega times t from omega because I don't have any t in the image of phi 1. So to get omega times t, I have to add it in manually, and to get this ideal that's circled in red, I'm going to need to put in all the omega times t to the I. So I need infinitely many generators, which tells you that I do not have ACC on ideals of the center. But then once I fail to have the ascending chain condition on ideals of the center, you obviously don't have the ascending chain condition on the two-sided ideals of the image of phi 1. So this is the proof that the image of phi 1 is badly behaved, and therefore that my original ring, enveloping algebra with loop algebra, also the two-sided ideal structure is badly behaved. So what about the interesting, or the harder part of the theorem, maybe, the structure that we do have on two-sided ideals? So let me go back and just remind you what that third part is that I now need to worry about the proof of. The third part says that any two-sided ideal contains the kernel of some phi L. So I want to spend the rest of the talk talking about how that is proved. So we want to study two-sided ideals, and they're complicated, right? I mean, we know they're complicated. We just proved that the lattice of two-sided ideals is not Noetherian. So I want to find simpler structures that are related to two-sided ideals of my enveloping algebra. So I'm going to use, I'm going to look at some sub-Lie algebras of my loop algebras. I've got capital E, which is loops on the element little e, if you will. In other words, it's elements that look like e times a Laurent polynomial. I've got capital H, which is loops on little h, which is h times Laurent polynomials. Now, E is, of course, a subspace and a sub-Lie algebra of the loop algebra, and it's abelian, right? E s to the I bracket E s to the j is E bracket E times s to the I plus j, but E brackets E is 0. So we have this big infinite dimensional abelian Lie algebra sitting in our loop algebra. So therefore, the enveloping algebra of this capital E sits inside the enveloping algebra of the loop algebra. But I just said that E is an abelian Lie algebra. So the enveloping algebra of capital E is actually the same thing as the symmetric algebra on capital E. In other words, it's a giant polynomial ring in infinitely many variables. Now here we have to change notation. Right. The basis I've given you for capital E is the basis is E s to the I, where I is in Z. But you're going to one is going to get confused if you try to look at an element of an associative ring written E s to the I, because you think you've got an E and an S and you're multiplying them. So I'm going to I'm not going to talk about E s to the I anymore. Instead, I'm going to refer to that element as E parentheses I. And so I've got, sitting inside the enveloping algebra of my loop algebra, I've got the enveloping algebra of capital E, which is a giant polynomial ring in all of the E round brackets I, for where I is any integer. So why is this helpful in understanding two-sided ideals of the enveloping algebra of the loop algebra? Well, let's take a two-sided ideal of the enveloping algebra of the loop algebra, and let's call it J. Then I'm going to tell you two things about the intersection of J with S of E, this big polynomial ring sitting inside there. First of all, that intersection is non-zero. J intersect S of E is non-zero. Why is this? Well, there's a map from S of E to the enveloping algebra of the loop algebra mod J, right? I take S of E, I include it in the enveloping algebra of the loop algebra, as I've said at the top of this slide, and then I factor out J. But we've seen in one of the theorems from the paper with Becker-Biswell that U of LSL2 factored by J has finite growth. On the other hand, the polynomial ring in infinitely many variables was an example of a ring with infinite growth. So that tells you that this homomorphism we've got from S of E to this ring with finite growth can't be injective. It has to have a kernel. And that kernel, of course, is precisely J intersect S of E. So, I mean, I guess this tells you more. Not only is there an intersection, but this intersection is big, right? In the same sense that ideals of the enveloping algebra are big. J intersect S of E is so big that it knocks this polynomial ring in infinitely many variables down to something with finite growth. But we don't need to know that it's big. We just need to know that it's non-zero. So that's one thing we know about the intersection of J with S of E. There's another thing we know, though, and this comes from the fact that two-sided ideals are closed under commutators. So let's take some element theta in our ideal J. Then it's a two, and let's act on it by left and right by hi, which is how I'm now writing the element that I used to call hs to the I. So this is some element of the loop algebra. So hi times theta is in J because J is a left ideal. Theta times hi is in J because J is a right ideal. So their difference is in J. So in other words, J intersect J and J intersect S and E, S of E, are preserved by the adjoint action of H. And I should note here that capital H acts on S of E by the adjoint action. So S of E is naturally... Yeah, something weird going on. I'm going to just forge ahead. So let's look just at H ideals. So this suggests, if you want to understand two-sided ideals of the enveloping algebra of the loop algebra, well, a good start is to start by trying to understand H ideals of S of E. So H ideals of S of E have intrinsic structure, and one of the nice structures they have is they're automatically graded, and furthermore, the graded pieces are all H subrepresentations. So let's talk through that. Remember, capital H acts on E by the adjoint action. This is, HI acts on EJ to give 2 times EI plus J. Is the bracket in the loop algebra. So therefore, capital H acts on the symmetric algebra of E. And let's look, and when you look at what H0 does to a monomial of degree k, so a product of k of the e's inside S of E, it's going to end up multiplying that monomial by 2 times k. So what that tells you is that the graded pieces of S of E are all eigenspaces for the adjoint action of H0. And then it's standard that because H acts semi-simply on S of E, that any H subrepresentation needs to decompose as a direct sum of eigenspaces. In other words, these graded pieces of the ideal I. So this suggests a further reduction to our problem. We started by worrying about two-sided ideals of the enveloping algebra, loop algebra. We then realized, well, actually, let's just figure out, we can get out some information by looking at H subrepresentations of S of E. And now we've realized, well, actually, there's H subrepresentations just of the individual symmetric powers of E floating around, which are the graded pieces of J intersect S of E. So let's set up some notation to talk about what H subrepresentations of the kth symmetric power of E look like. First of all, in the lemma above, I was writing I sub k, and so effectively I was treating E as a graded ring where all of the EIs had degree 1. In that notation, the degree k stuff in S of E is precisely the kth symmetric power of E. So I'm going to usually write that as S exponent k of E. So we want to understand the H action on Sk of E. And it turns out to be easier to look at not at sk of e at the kth symmetric power of e, but at the symmetric invariance of the k-fold tensor product of e. So these two vector spaces are naturally in bijection, but I want to be careful about them because the kth symmetric power of E is naturally thought of as a quotient of the k-fold tensor product of E. In other words, I take, say with k equals 2, right? I've got, an element x and an element y, and to look at the second symmetric power, I've declared that x tensor y and y tensor x are the same thing. So that's a quotient of E tensor E. On the other hand, what I'm writing as sim k of E, these are going to be tensors, elements of E tensor k, E tensor 2, that are invariant under swapping the variables. So an element of sim 2e might look like x tensor y plus y tensor x. Right. Now I can go back and forth between these two things. There's natural maps back and forth. I'm not going to write those down terribly carefully. I just want to keep track of when it turns out to be a lot easier to work in the subspace of E tensor k rather than the quotients. So that's what I'm going to use. So I wanted to think about H subrepresentations of sk of E, but instead let me look at H subrepresentations of the kth symmetric power of E, sim ke. So I'm actually not going to think about sim ke for a second. I'm going to think about this ambient space, the k-fold tensor product. And I can naturally put the k-fold tensor product of E in bijection with Laurent polynomials in k variables, which I'll call here x1 through xk. And I'll call that ring zk. And there's a map that goes from E tensor k to zk, which I'll call zeta sub k because it goes to z. And there's a map that goes from zk to the k-fold tensor product, which I'll call tau sub k. So what's this map? Well, it sends a natural basis to the natural basis. So an elementary tensor in E tensor k looks like ei1 tensor, tensor ei2, tensor out through tensor eik. And I'm going to map this to the monomial x1 to the i1, x through xk to the ik. So this is telling me, the x1 to the i1 is telling me that my first E is shifted by I1, and then my kth E is shifted by IK. So there's a natural action of H on E and therefore on E tensor K. And here's what Hj does to this elementary tensor ei1, tensor eik. Right? It acts on each tensor end, and on each tensor end it adds j to the shift, the loop variable. So it sends ei1 to ei1 plus j, and of course it multiplies by 2. So it does that for all of the tensor ends, and so I get a k-fold sum, which I've written down here. So I'm going to use this map, these maps zeta and tau, to just move that over to the right-hand side and write down the corresponding action of H on my polynomial ring zk. So to figure that out, right, I just need to say, well, where does zeta send this sum of k terms, which was hj times my elementary tensor, and it sends it to xi1 through x1 to the i1 through xk to the ik times 2 times x1 to the j out through xk to the j. So again, of course, a sum of k terms. And the thing to notice here is that I've multiplied my original monomial by a symmetric polynomial. This x1 to the j out through xk to the j is in the invariant ring of zk under the action of the symmetric group on k letters. So I've just talked about the action on E tensor K, but when you look at what happens at the subspace sim K of E, which is the symmetric stuff inside E tensor K, then H subrepresentations of sim K of E under this bijection corresponds precisely to ideals of symmetric polynomials, right? Because acting on an element by something in capital H corresponds to multiplying that element by a symmetric polynomial. So the H structure on sim K of E is really nice. It's just ideals in this well understood nice commutative ring. And you can soup this up to get to look now not just at a subrepresentation of Sk of E, but let's look at an H ideal of S of E, and let's call that I. So what we're going to get is not an ideal of an invariant ring, because we're going to wind up on the right-hand side in Laurent polynomials and infinitely many variables acted on by the infinite symmetric group. And of course, there's no invariance, but we can we can look specifically at symmetrically invariant ideals of this big Laurent polynomial ring. So ideals that are invariant under the action of the infinite symmetric group. And we can get such a S infinity invariant ideal from our H ideal I in the following way. This is a procedure which I'm going to call capital theta. So I take my I look at the graded pieces of I. For each ik, I map it by zeta k into zk, polynomials in k variables. I then look at the ideal of z infinity generated by those invariant polynomials. Then I close it up under the action of the infinite symmetric group. So now what I'm going to have is I'm going to have an ideal of z infinity that is invariant under the action of the infinite symmetric group. Now the good thing, this is sort of a complicated procedure, but the one good thing about it is that S infinity invariant ideals of Z infinity are well understood and really nice. We finally get something that has a good structure. And so let me tell you about that, and let me tell you also about these discriminant elements, which will turn out to give the key not only to S infinity invariant ideals of Z infinity, but also to H ideals of S of E and to two-sided ideals of the enveloping algebra of the loop algebra. But let's start with S infinity invariant ideals of Z infinity. So this is a theorem that goes due to Cohen back in the 60s, extremely classical at this point. So Z infinity, of course, not Noetherian, hard to get a handle on, but symmetrically invariant ideals, ideals that are invariant under the infinite symmetric group, do satisfy the ascending chain condition. So there's a lot of structure there. And secondly, suppose I've got a non-zero symmetrically non-zero S infinity ideal, invariant ideal of Z infinity. Then it has to contain some element I'll call a discriminant. So you've got these elements P sub L, which are just, I take the first L variables and I take the product of all their differences. So this is, I don't know, I guess some sort of van der Waals determinant, or I mean, these are elements one looks at, of course, when you want to ask questions like, does a polynomial have repeated roots? And one of these discriminants has to be in my two-sided ideal K. So let's recap, right? I wanted to understand two-sided ideals in U of LG. I have figured out, I've reduced, I'm worrying about a simpler problem, which is worrying about H ideals of S of E. And I can, from an H ideal of S of E, there's this procedure theta that gives me ideal of Laurent polynomials and infinite many variables that is invariant under the action of the infinite symmetric group. And such ideals have a very nice and very well understood structure. So what does that very nice, well understood structure on symmetrically invariant ideals of Z infinity, what does that tell us about H ideals of S of E? Well, first of all, this procedure theta that we had, complicated procedure theta we set up in the previous slide. From an H ideal, get an S infinity ideal of Z infinity. It's not bijective, so you're going to lose a lot of information going from H ideals to ideals of Z infinity. However, we can still deduce from Cohen's theorem that S of E does satisfy the ascending chain condition on H ideals. And furthermore, there are these discriminants in S of E that play a similar role to the discriminants in Z in Z infinity. So let's go back to the definition of the discriminant. These discriminants PL. Remember, any symmetrically invariant ideal of Z infinity contains one of these PLs. How do we get from PL to an element delta L in S of E? Well, PL is an element in my polynomial ring in L variables. If I square it, it now becomes invariant under the action of the symmetric group on L letters. I can therefore, now I've got something that's, now I've got a symmetric polynomial. Symmetric polynomials are in bijection with symmetric invariance in my L-fold tensor product under my bijection between the polynomial ring ZL and E tensor L. So this PL squared goes to an element I'll call DL in the symmetric element in my L-fold tensor product. And then finally, there's a natural bijection between the symmetric elements of the L-fold tensor product and the Lth symmetric power. So I get an element delta L in my Lth symmetric power in my SL of E. And the third part of the proposition is that any H ideal of S of E contains one of these discriminants, delta L. So let me tell you, let me show you what happens for just L equals 2, just to get a handle on what these elements look like. So the discriminant in Z, in this case in two variables, is just x1 minus x2. To get a symmetric invariant, I need to square it. So I get x1 squared minus 2x1 x2 plus x2 squared. I now need to move it over to the tensor square of E, or to the symmetric stuff inside the tensor square. So x1 squared, right? I got 2 copies of the first e and 0 copies of the second one. So that's e2 tensor e naught. x1, x2 is e1 tensor x1, tensor e1, and x2 squared is e naught tensor e2. So what I get is e2 tensor e naught minus 2e1 tensor e1 plus e naught tensor e2. And then I move that over to the symmetric square of e to get delta 2, which when I symmetrize this element, I get 2 e naught e2 minus e1 squared, it turns out. So that's an example of one of these discriminants. And let me notice that phi 1 sends this element to 0, right? Phi 1 sends ei to et to the I, so it sends ei ej to e squared t to the I plus j. So it's going to send e naught e2 and e1 squared both to e squared t squared. So it's going to send delta 2 to 0. And in general, you can show that delta L plus 1 is in the kernel of this map phi L. So we now have enough stuff so that we can prove our theorem that says that any two-sided ideal contains the kernel of some phi L. So let's take a two-sided ideal of the enveloping algebra of our loop algebra. Let's call that J. And J intersect S of E is an H ideal of S of E, we've seen. And we've also seen a couple of slides ago that any non-zero H ideal contains some delta L. So we've got some delta L sitting inside our two-sided ideal J. So J contains the two-sided ideal generated by delta L, but then one shows that the two-sided ideal generated by delta L contains the kernel of some phi map. It actually contains the kernel of phi 3L. So there's the proof of the structure that we do have on two-sided ideals. And a similar thing is going to work starting with any finite dimensional Lie algebra G, except the number 3 is going to get replaced by the dimension of G. So I'm almost done, but there's one more thing I wanted to point out, which is the following corollary. Take a finite dimensional representation of a loop algebra. Right. Well, it has a non-zero annihilator, which is a two-sided ideal of the enveloping algebra of a loop algebra. Therefore, by the theorem, it contains some kernel of phi L. In other words, there exists L such that the kernel of phi L is contained in the annihilator of our representation W. Now, once you know this, it's not hard to prove this directly, but this seems not to be known. As evidence for the fact that this wasn't known, I asked Vijayanti Chari if something like this was true when I visited her a year ago, and she didn't think it was. So that's all I had. Thank you very much.
Great. Thank you, Sue. That was a very nice talk. Are there any questions for Sue? I was wondering when you take something other than SL2, when you were talking about the Casimir, do you like when you talk about the center, for other finite dimensional Lie algebras, the center in general is larger than just the Casimir. Do you need to consider those two, or is it enough to just consider the quadratic Casimir?
So the center for other Lie algebras is, I guess, by the Harishchandra isomorphism, it's a polynomial ring generated by all of the generalized Casimirs, right? Um, and the same kind of thing is going to happen. You could get um, any of the generalized Casimirs times any power of t, but you can't get t by itself. So I guess I guess you got a choice. You've got choices therefore of what you want to take as your example of an infinitely generated two-sided ideal. But for example, you could just take, um, you know, the ideal generated, I guess, by the quadratic Casimir. And again, that sorry. Let me speak more precisely. Let me actually go back and tell you what I'm talking about because I don't want to. I'm talking about generators. I'm not saying what ring I live in. So with the SL2 proof, right? I mean, I was looking at the ideal of the center of the overring, Laurent polynomials over USL2, generated by the quadratic Casimir, right? But if I thought about, and that is inside the image, and similarly, quadratic Casimir times the center of the overring is going to be inside the image, but it's not going to be a finitely generated ideal of the image.
Yeah, thanks. Any other questions for Sue? Okay, let's thank Sue once again for the very lovely talk.
Welcome. And again, I'm sorry about the technical issues with the talk. Thank you for bearing with me. I guess I'm gonna sign off. I didn't realize. It took me a little while to realize you were in charge, Lee. Because sorry, because I was flustered by dealing with my tech issues.
That's okay. Yeah,
So
it's a really nice talk.
you're in California at the moment,
That's right. Yeah, yeah, yeah.
so you got up early.
I mean, yeah, I've been getting up roughly around that time anyway. It was 8 a.m. when it started, so